Okay, let's start the afternoon session. This is Akran Baba. I am chair of this session. Okay. And first speaker is Professor Yuichiro Sato from Waseda University. His title is the Construction of Higher Dimensional Vacuum Solutions Using Almost Abelian Groups. Please start.
Thank you for introductions. Also thank organizers for giving me the opportunity to talk in this conference. First of all, I have a souvenir. My souvenir is over there. It is onsen manju. Please enjoy. Okay. And today I'd like to talk about higher dimensional vacuum solutions of Einstein equation using almost abelian groups. And this talk is based on joint work with Takanao Tsuyuki, who is not a mathematician, but an expert on particle physics. Ah.反応もしない。そうですね。多分。ええ。でもこれ OK なの？ああ、はい、そう。今これご自身の。これ私のですね。一回ちょっとタッチ。あ。あ。Okay, so roughly speaking, our results is a two generalization of the classical solutions. The one is the tab solutions, which has this formula or structure. It is from the first paper, which is circled one. And the other is a generalization of the Petrov solutions, which has this homogeneous structure. It is from this preprint, which is circled 2. And this is contents in my talk. First of all, I make introductions, and next I will explain special homogeneous spacetimes and homogeneous spacetimes. Finally, I will raise some problems. Okay, let's M and Gn be an n-dimensional Lorentzian manifold. For simplicity, we call it spacetime. As you know, the Einstein equations are given by these blue equations. Left-hand side is a rich tensor minus scalar curvature over 2 times the metric Gn, plus the capital lambda times the metric. This is so-called cosmological constant. This is the left-hand side. On the other hand, right-hand side, it is a meaning in physics. T, it's just noted by capital T. It is called energy momentum tensor. So this means matter. So this means the density of the matter in the our universe. In this talk, we will focus on vacuum Einstein equations. That is, these equations are given by just this. So namely, in case T and capital lambda are 0 case. So mathematically, if spacetime satisfies the vacuum Einstein equations, then we call it a vacuum solution. So mathematically, it is equivalent to Rich flat. So this, if a space-time satisfies the Rich flat conditions, it is also a vacuum solution. So if you find vacuum solutions, we have only two construct or find a rich flat Lorentz manifold. From now on, let me explain some vacuum solution, some examples. The most typical example is the Minkowski space-time. It is defined by like this. So as you know, this example is just flat Lorentz manifold. And also, it is the stage of special relativity, which was founded by Albert Einstein. And the next one is the Schwarzschild spacetime, or so-called Schwarzschild solutions, which is defined by like this. So as the manifold, M is equal to the time interval R cross the R3 removed closable B, and the metric GM is equal to this metric. This solution implies or means the existence of black hole in theoretically. Of course, we can observe the black hole, in fact. And the third one is PP wave spacetimes. So it is defined by this. So locally, the manifold is just R4, and the metric is like this. So here, the function capital H is a function with respect to 3 variables, U, X, and Y. Here, this function capital H must satisfy this harmonic condition. Of course, PP wave spacetimes, PP wave solutions are vacuum solutions of Einstein equation. PP wave spacetime means gravitational waves. So recently, we succeeded the observation of the gravitational wave, maybe around 2050 or maybe 2054, around there. And finally, I want to explain the Kastner spacetime or Kastner solution. As a manifold, M is equal to this interval from 0 to infinity, and times R3. And the metric GM is equal to this metric. So there are 3 parameters, P1, P2, P3. These parameters satisfy 2 equations. And the Kastner spacetimes means anisotropic universe without matter. So because for 3 parameters, P1, P2, P3, 2 parameters of them must be positive. The last one, the other parameter must be negative. So for example, P1, P2 are positive, but P3 is negative. So if you see this part, we can observe the expansion or construct of space. So that's why we say anisotropic universe. Here, there are 2 important points. The first one is these solutions, which are explained, are 4-dimensional exact solutions of the vacuum Einstein equation. So we expect the higher dimensional case of these solutions. And another point is Kastner spacetime. These solutions have special homogeneity as an additive Lie group. I mean, so this interval means the time. On the other hand, this part, R3, means the space of the space-time. So R3 has a one-parameter family of left invariant Riemannian metric. So I mean, so additive Lie group is R3. So we can replace R3 as other Lie groups. And this is this is known as cosmological principle in physics. In physics, there are no preferred places in space. It is translated in the notion of spatially homogeneous in mathematics. Moreover, in physics, there are no preferred direction in space. It is translated in translates as spatially tropic in mathematics. So in terms of the particle physics, we want to consider the higher dimension spacetimes. In particular, we expect to obtain 10-dimensional or 11-dimensional spacetimes. These spacetimes are related to string theory or M theory in physics. Okay. So here we will move on the explanation of spatially homogeneous solutions. Let I be an open interval and G a one connected Lie group. And now we consider the following spacetime. As the manifold M is equal to the product of I and G, and as a metric Gm is equal to minus n squared dt squared plus Gg of t, where capital D, this is a positive function on R. This is a function with respect to the time t. And GGT is a one-parameter family of a left invariant Riemannian metric on G. So by definition, this spacetime is trivially spatially homogeneous because we consider left invariant Riemannian metric on G. So I mean, for any 2 points, x and y, in the space G, there exists isometry left translation, which maps x to the y. So that's why this is trivial spatially homogeneous. As a remark, when the dimension of G is equal to 3, the spacetime is called the Bianchi spacetimes in the general relativity. So this terminology comes from Bianchi classifications. A Bianchi classification is a three-dimensional, the classification of the three-dimensional Lie algebra, equivalently three-dimensional Lie groups. So there are, roughly speaking, there are 9 types from type 1 to the type 9. I will explain later, but from type 1 to type 7 are almost abelian, but the other are simple. Okay, so and let G be the Lie algebra of the given Lie group. And this set x1 to the xn, a set of the generator of gay. So I mean, this is just the basis of gay. So in general, the spatially homogeneous spacetime, the previous spacetime, can be expressed as the blue formula. So here, omega 1 to omega n are left invariant one forms on the Lie group G. So next, let capital N and A1, A2, blah, blah, An be positive functions on the open interval I. And we consider a spacetime with the following diagonal metric. So diagonal metric means the metric Gn can be expressed this one. Where A1 to the An are called scale factors of the space. So here I should mention, this is, of course, this metric is a special case. In general, the metric can be expressed like this. So, but for simplicity, we assume the diagonal metric. Anyway, so in such cases, we can compute the rich tensor of the spacetime. But here, we do not remember this formula. What I want to say is that using the structure constants of the Lie group and functions such as capital N and the scale factors A1, A2, An, we can compute the rich tensor like this. So if we find the rich flat manifold or vacuum solutions equivalently, we have only to solve the equations. This is equal 0, this is equal to 0, this is equal to 0. That's all. Okay, so here, let me explain the moduli space. Let capital G be a one-connected n-dimensional Lie group. The moduli space of left invariant Riemannian metric on G is given by this double coset as a set. But here, please see this identification. So that is, this moduli space is homeomorphic to this space. Here, this symbol, sim n plus nr, denotes the means metric space of Lie group, because we consider the left invariant Riemannian metric on G. So that's why. So this sim n plus r means the space of the metric. And here, aut of G denotes the automorphism group of G. This group acts on naturally this metric space. And L greater than 0, this is just positive numbers. This group, this additive group acts on this set by scaling of the metric. As a topological properties, the moduli space is a connected and Hausdorff space. And the points corresponding to principal orbits form a smooth manifold. That's why it makes sense the dimensions of the modular space. In particular, the dimension of the modular space is equal to 0 if and only if the modular space is a singleton, as I said. So here I will explain. Theorem 1, which was proved by Rore originally, and Kodama, Takahara, Tamaru, they introduced the notion of the modular space of F3 inverted Riemann metric. The statement is the following. The dimension of the modular space is equal to 0 if and only if the Lie group is isomorphic to one of the three cases. The one is Rn, it is just abelian. And Rhm, it is a m-dimensional real hyperbolic space with a Lie group structure. And H3 times some additive Lie groups. Here, where H3 denotes three-dimensional Heisenberg group. So that's why we already obtained the classifications of Lie group whose modular space has zero dimension modular space. And here, I wanted to find the almost abelian Lie group. So what is the almost abelian Lie group? Z is almost abelian if there exists codimension 1 abelian ideal in G. G is the Lie algebra of G. So by definition, there is a one-to-one correspondence between the set of the isomorphic classes of almost abelian Lie groups and the set of equivalent classes of real square matrices. For two matrices A and B, A is equivalent to B if A is similar to B up to scaling. I think it is natural equivalent relation of real square matrices. And as a remark, a Lie group is almost abelian, then it is meta-abelian. Equivalently, it is just a two-step solvable. Okay, so moreover, two-dimensional Lie groups are all almost abelian. But for three-dimensional cases, are classified to types. One type, of course, almost abelian. So the other types is semi-simple. And these situations, I mean, the dimension of modular space go to 0. Then such Lie groups are almost abelian. So for example, when the Lie group is equal to Rn or Rhm or H3, three-dimensional Heisenberg group, these are almost abelian. So there exists corresponding square matrices A. Such matrices A is equal to 0 matrix and identity matrix, and this Jordan block, namely 0, 1, 0, 0, respectively. So anyway, we can take these matrices as representative elements. Okay, the following is known as four-dimensional exact vacuum solutions of Bianchi type 2 spacetimes. this is classical solutions in general relativity. So it is theorem 2, which is found by Terp in 1951. A spatially homogeneous spacetime, this type spacetimes. So as a space, we choose three-dimensional Heisenberg group. And it is called a Bianchi type 2 spacetime. I forget some remarks. So a Kastner solution, it is type 1, Bianchi type 1 spacetime. Okay, so anyway, it is rich flat if and only if by taking suitable coordinates, this metric can be expressed like this. Anyway, we can get expressions explicitly. So this solution is called the Terp solution. Okay, so now we generalize the Terp solutions in the following sense. As I said, that this Lie group is almost abelian. So the corresponding matrix A is equal to just this Jordan block. And so here we want to consider this group as a higher dimensional case. Of course, the corresponding matrix A is equal to the direct sum of the Jordan block and their matrix. Here, this is a table of vacuum solutions of spatially homogeneous spacetime. When n is equal to 3, it is just Bianchi spacetime, as I said. For R3, it is Kastner solutions. And RH3, it is already obtained the exact solutions by Joseph in 1969. And H3, in the case of H3, it is Terp solutions, as I said. So how about higher dimensional cases? Chodos and that wire generalized Kastner solutions. And also, Debre and Hankin generalized Bianchi type 7 solutions in 1985. So our first result is here. This is the main result, well, 1. In case the space G is equal to this Lie group, the spatially homogeneous spacetime is rich flat if and only if it is isometric to the Lorentzian metric. So we can obtain the expressions of the vacuum solution explicitly. Of course, when n is equal to 3, these solutions in this Terp solution. Okay, so what is the difficulty of this theory? In general, we cannot necessarily diagonalize the metric, of course. So to overcome it, we use the moduli space of the metric. So how to use? One, if the moduli space is homeomorphic to this diagonal form, the initial metric, like C of T0, the T0 means initial time, can be diagonalizable by isometry, such as, isomorphism of Lie group. And 2, by the freedom of the coordinates of space, the velocity of the metric g dot t0. This means time derivative of the metric. This metric can be diagonalizable. 3, let's find the solutions under the diagonal metric because our vacuum Einstein equations are the second order ODE, ordinary differential equations. But we should remark the vacuum equations are overdetermined. So in general, maybe when pick up some Lie groups, then maybe there is no solutions in vacuum Einstein equation because the Einstein equation are overdetermined. However, these 3 cases are fine, and also, so for these Lie groups, the moduli space homeomorphic to the singleton. Equivalently, it is equal to homeomorphic to this one-point set. So namely, so this moduli space has the form like this. As a corollary, we already the explicit expression of the vacuum solutions. So we can see the behavior of the space-time in time evolution. I mean, of course, so obtain the solutions are spatially homogeneous, but not spatially isotropic. Moreover, each of spatial dimensions cannot expand or shrink simultaneously in the late time limit like this. So this is one example of our solutions. So here I should remark, here just we take special initial values. So if we take a special initial values, then such solutions this has this behavior. So I mean, so this is a 11-dimensional spacetime, and for 10-dimensional space, three dimensions are expanding like this, but the other dimensions of space are shrinking like this. Okay, so next I will explain simply homogeneous solutions. Let capital G be a one-connected n-dimensional Lie group, and G the Lie algebra of G, and G sub G are left invariant Lorentzian metric on G. Here we consider the Lorentzian metric on the Lie group. As you know, there are one-to-one correspondence between the set of the left invariant Lorentzian metric on the Lie group and the set of the symmetric bilinear form on the G with Lorentzian signature. Of course, this pair is a homogeneous Lorentzian manifold. And as a remark, Carvalho and Zain classified 4-dimensional Lorentzian Lie groups, of which are Ricci flat, Einstein, conformal flat, and so on. But they use the computer to obtain these Lorentzian Lie groups. And this is a difference. Okay, here, how about the classification of Lorentzian homogeneous manifolds? So the most typical examples are Lorentzian space forms. They are Minkowski spacetime, digital spacetime, and anti-digital spacetime. These are analog to Riemannian space forms, such as Euclidean space, round spheres, and real hyperbolic spaces. Of course, it is homogeneous, Lorentzian homogeneous manifolds. And next, we want to consider Lorentzian symmetric spaces. For these spaces, we already obtained the classification of Lorentzian symmetric spaces. There are two types. The one type is the Lorentzian space forms, and the other one is so-called Carhan-Wallach spaces. This space is solvable symmetric spaces. So this phenomenon never occurred in the Riemannian geometry. So in shear Riemannian geometry, like Lorentzian geometry, so such spaces quite often appears like this. So in general, how about the Lorentzian homogeneous spaces? Of course, there are many results about these topics. Here, I will explain one important result. Let G be a simple Lie group, and G acts on the Lorentzian manifolds isometrically and non-properly. So here, non-properly means the isotropy subgroup or stabilizer is not compact Lie group. And here, we do not assume this action is transitive. But then G is locally isomorphic to these indefinite orthogonal groups. So anyway, the local isomorphic classes of G is completely determined by the result. So my question is, can we classify Lich-flat Lorentzian Lie groups? The following is known as only 4-dimensional vacuum solutions whose isometry group acts simply transitively. So this is theorem 3, which was proved by Petrov in 1962. The only 4-dimensional vacuum solution admitting a simply transitive maximal group as its isometry group is given by the metric, this Lorentzian metric. This solution is called the Petrov solutions. For these solutions, the King vector fields are given by these 4 vector fields. So by using these vectors, we can compute the brackets of the vector fields. Then we can see the isometry group is almost abelian. So that's why we generalize the Petrov solutions in the area of almost abelian Lie groups. Here, this is an important lemma in my talk. Let G be an n-dimensional almost abelian Lie group, and G sub G are left invariant Lorentzian metric and Lie group G. Then there exists a basis of the algebra K, so from x1 to xn minus 1 and xn, such that x1 to xn minus 1 span the abelian area of G, and the real algebra G can be decomposed as a semi-direct product of the abelian ideal R and the one-dimensional line. And the bilinear form, this is with the Lorentz signature, can be expressed by the following three types by using the basis. The case A means the restriction of the metric, the restriction of the bilinear form on R is Riemannian. That is positive definite inner product. And case B means the restrictions on R is Lorentzian. So it has a Lorentzian signature. And the case C means the restriction on R is degenerate. Okay. By using the previous lemma, we obtain the next main result to let the pair be an almost abelian Lie group with left invariant Lorentzian metric. In case A metric, if this homogeneous space is Ricci flat, then it is just flat. I think it is a trivial case. In case B, decomposing A as SL and TL, such that SL, the part SL, satisfies these equations, and TL, this part, satisfies these conditions, where J is following diagonal matrix minus 1, 1, 1, 1, and 1. Yes. So if J is simply the identity matrix, then these conditions mean symmetric and skew symmetric matrices. I think these conditions are the Lorentzian analog of symmetric matrices and skew symmetric matrices. Anyway, so when decomposing the A like this, then this homogeneous space is Ricci flat if and only if it holds the three conditions. That is, the trace of SL and SL squared are 0, and SL is commute TL. But finally, in case C, if the homogeneous space is Ricci flat, then it is a plane wave. So a plane wave is a PP wave, as I said in the introductions in my talk. So, but in general, a plane wave, the isometric group of the plane wave has a non-trivial isotropic subgroup. I mean the isotropic subgroup has a non-trivial. So how to say? So the dimension of the isotropy subgroup is greater than or equal to 1. So that's why I explained it has a non-trivial isotropy subgroup. It is not trivial. Okay, so as I said, the Petrov solutions has the isometry group X on the underlying manifolds simply transitively. So, however, in case A, it is a flat case, and in case C, these situations, rich flat situations, implies it must be a plane wave. The plane wave has these properties. So we will remove this case A and C. So that's why we find the generalization of the Petrov solutions in case B. But what is the difficulty of this theory? Of course, it is, in general, it is hard to solve the rich flat condition in case B. So I mean, so this is a simple expressions, but in general, it is hard to solve these equations. To overcome it, we consider isometric classes and normal forms of the matrix. How to consider? One for the decomposition, like this. So the part, the skew-symmetric like matrix part, does not affect on the metric. So we may forget this part because so this matrix means structure constants of the almost abelian. So this matrix determines the structure of the Lie group structure. But here we want to consider isometric classes of as a Lorentz manifold. So this part does not affect on the metric. We can forget this part. And two, anyway, from one, A is just equal to symmetric like part, SL, just SL. And this SL has a normal form in the sense of the Lorentzian transformation. It is not orthogonal transformation. Such transformation preserves the metric in the case B metric, and the rich flat, of course, rich flat condition. So as 3, we have only to find the solutions for each normal forms of these matrices. Roughly speaking, such normal forms are classified like this. So I mean the normal forms is a diagonal sum of a diagonal matrix and these three matrices. Okay, so as a corollary, we obtain the following. Let G and GG be indecomposable and non-flat and rich flat almost abelian with left invariant Lorentz metric. Then this homogeneous space admits an almost simply transitive isometric group, if and only if it is isometric to the Lorentz metric. And here the word indecomposables corresponds to the red equation formula, and the rich flatness corresponds to these two equations, and this part, orange ones, corresponds to this condition. So here I should mention that we cannot remove the word of almost, because here we just consider full isometry groups. So in this case, the entropy subgroup of isometry group is not trivial. But the structure of the entropy subgroup is just the power of Z2. Or taking special parameters, the structure of the entropy subgroup is isomorphic to D4 times sum of some Z2, where D4 denotes the dihedral group of order 8. So anyway, the entropy subgroup is not trivial, but it is a discrete subgroup. So that's why we need the notion of the almost simply transitive action. Of course, when the n is equal to 4, these solutions induce a Petrov solution. Okay. At the end of my talk, I will raise some problems which are related to our research. The terminal spacetimes, it is given by this Lorentz manifold. As a manifold, it is a time interval R and S3. S3 is just a three-dimensional sphere, and with this Lorentz metric. This solution comes from the following Bianchi type 9 spacetime. Type 9 corresponds to the semi-simple Lie group, say SU2. It is just a special unitary group with order 2. So anyway, this solution comes from this spacetimes. So here, please see this metric. Here, omega 1, omega 2, omega 3 are left invariant one forms on the special unitary group. And here, these functions are called scale factors of the space. And here, we assumed that this one and this one is the same. That the third one is different. So in such cases, these solutions appear. So the question is, can we find the exact solutions of the general form? I mean, the scale factors are all distinct. Yes. Even if this is a four-dimensional case, we cannot find the exact solutions of this one. But of course, there are numerical solutions. So yes, there is a numerical solutions, but analytic solutions is not succeeded. Okay, so of course there are many problems. first one, can we construct vacuum solutions using other Lie groups? Today, we use Lie groups whose moduli space has 0 dimension. So in particular, for example, how about compact Lie groups? And I'm interested in these problems. So can we classify the Lie groups whose automorphism group contains the orthogonal group SON? If this condition is satisfied, the moduli space of the metric is homeomorphic to this diagonal form. So then we can apply the vacuum Einstein equation. Okay, so our next one is can one consider the case of homogeneous spaces in the same way? So for example, symmetric spaces. So in such cases, maybe we have to consider the structure of the moduli space of G invariant Riemannian metric, because the symmetric spaces, in general homogeneous spaces, has a double coset expression like G over K or G over H, like that. Finally, can one discover, in general, Ricci-Flat or Einstein Lorentzian Lie groups? So of course, we can consider Einstein almost abelian Lie groups. Today, we consider the Ricci-Flat almost abelian Lie groups. And besides, it is also, so we are interested in the Einstein-Yang-Mills equations on homogeneous spaces. So the Einstein-Yang-Mills equations means Einstein equations and, of course, Yang-Mills connections. So Yang-Mills connections is related to the how to say, communicating. So I don't know how to say. So sorry. So Yang-Mills connections is related to physics. So how does the force communicate in the world, real world? Okay, this is the problems which one I want to explain. Okay, so it is almost time. So I stop here. Thank you for your attention.